good afternoon, good evening, whatever it may be. Look, we've already got a good crowd here. We can get started. So this is going to be a code walkthrough of Crush, one of the fundamental building blocks of Ceph. And Sage, I think there's lots of kind of corners of Crush that haven't been changed in many years, so it'll be quite interesting to see what those look like and where they came from.
Yep. All right. Okay, so I think I might start with just like a really quick slide, a couple slides from the original Crush presentation actually that just show at a very high level how the algorithm works before diving into the code. But then just want to encourage everyone to like stop me and ask questions because it's always hard to tell which parts are most interesting to cover and what is clear and what is not clear. And also my headset will turn off if there isn't any sound coming through. So if somebody will ask a question, then it'll reset the timer each time. All right, so Crush does data placement. Everything in the cluster, of course, is organized as a hierarchy. And it's all based on, these placements are based on the placement rules. So this is just like a really simple illustration of how that works. So you have the initial command. These are the commands that form the rule. And as you're interpreting the rule, there's a working value, which is basically like kind of like a register, but it's an array of values that it's working on. So take root loads root into the value. Sorry, it's all crooked because this is a PowerPoint slide from a million years ago and I'm using LibreOffice. So first step, selects one row. There's only one starting with root. There's a bunch of rows beneath it. It'll pick one randomly, move that into the working value. Then the next rule, select 3 cabinets, distinct unique cabinets. We'll do that. And then each of these has those parts of the train beneath them. Here, when we select one disk, for each one of these working value items, it'll do that step. So for cabinet 21, it'll pick a disk, it'll do a disk, and so on. In this case, actually, it descends 2 levels of the hierarchy, both to get the disk array, and then also to pick a cabinet or a disk within each one. And it gets that. And then emit will just take whatever's in the working value and it'll spit it out into the final result. So that's the basic process of how the rules are interpreted. So let me share a window. All right, can everybody see that okay?
Yes.
Okay, all right, so I'll just start with the header file to go through some of the types. Crush.h, so most of the Crush code is written in C because it's identical code in the kernel and in user space. And then there's a bunch of stuff that's written in C++ that kind of like adds all the modifiers and stuff. The kernel code really just needs to be able to do the mapping and not much else. So there are a couple constants up here. There's a constant for an item that is undefined, and then you have, let's see, there's a structure for each step in the rule. These are all the different opcodes for the different rules for choosing items, omitting items, and so on. These let you adjust tunables for a particular rule, although most of the time you don't need to do that. I'll talk about tunables in a second. A rule is composed of a series of steps. It used to have these parameters that let you tell Crush what cases you should use that rule. These days we don't use, that's all deprecated. So really the only important fields are number of steps and the type. I don't even remember what the type is. I don't think we use it. Oh, it's like whether it's a replicated rule or a erasure code rule. I think is what that is, but it's mostly not used. Let's see, algorithm defines what algorithm we use when we're descending through each node. Originally, Crush was written to have 4 of them: uniform, list, tree, and straw. Tree was buggy and never worked, so we dropped that one. And straw, it turns out, was also incorrectly conceived, and so there's a straw 2 version that we use instead. These days, basically, we always use straw 2. I don't think anybody ever uses these other ones, and I wouldn't recommend them. And so I'll mostly ignore them. So most of the time, Ceph by default always creates straw buckets unless you like try really hard not to do that. or strat2. So that's the new type that everybody uses. Every bucket that's a node in the tree has an identifier. So there are two types of identifiers. Anything that's greater than or equal to 0 is a leaf node, like an OSD in Ceph's case, and everything that's negative is an identifier for a bucket. These go -1, -2, and so on. The type of bucket is the crush type. So that's whether it's like a rack or a host or a row or a data center or whatever those sort of user-defined types are. These are for users to describe. Algorithm tells you what algorithm to use when traversing that particular node. So this is almost always strat2. Hash function is always argjunctions. There's only one hash function defined. And then there are a couple items here. There are all the items, all the leaf nodes, basically, for this node. And there's a weight, which is basically the sum of all the weights for all the items. So normally the crush hierarchy always sums up from the leaves up to the top. So that's a bucket. Weight sets, I'm going to come back to later. So for the different bucket types, there are some additional fields that are type specific. So in uniform buckets, everything is the same weight. So there's only one weight. In the other ones, there's an array of weights. List buckets has this thumb thing. Tree buckets are totally bonkers, so we can ignore those. But for strat2 buckets, which is the ones that we mostly care about, it's really just there's this sort of parent bucket thing has the array of items, and then there's a weight for each item. And the only thing that's sort of weird in Crush that is a bit confusing when you're thinking about the code and stuff is that the weights, you would normally think about a hierarchy where the weight is a property of each item, and then they sort of sum up the tree. The way that Crush does it, the weight is always stored with the pointer at the reference. So the bucket has a list of all the items that are beneath it, and it also stores the weight of those items that it uses when traversing down, instead of actually storing the weight with the item, which is a little bit weird. But normally it's all identical. It's just stored in a different place, but it can be a little bit confusing. And then the Crush map has all the different buckets that compose the map, all the different rules, how big those arrays are. And then there are all these definitions that customize the behavior. So these are all collectively referred as tunables. Basically, when this was first written 15 odd years ago, there were a bunch of sort of weird behaviors that seemed to make intuitive sense at the time, but time has proven were bad ideas. And so all of these basically let you selectively disable all of those different annoying behaviors. And in a couple other cases, just make subtle changes to the algorithm, make it work better. And so when you create a new map, all of these are sort of set to the latest best practice. But old clusters might have values here that sort of keep doing the old behavior so that you don't reshuffle all the data. And I'll talk about some of those. And that's basically it. That's the Crush map itself. Questions on that?
You said you're going to talk about the tunables later, right?
Yes. Yep. I'll sort of sprinkle those in as we sort of go through the actual placement. So I think I was going to go through the do rule part, which is the actually calculating the placement.
Mm-hmm.
And I'll mention the different tunables there. So mapper is the sort of the core piece of code that's shared between the kernel and user space. It's the thing that actually calculates the placement. And the root of that is do rule here, which is actually calculates. You give it a map, which rule, input X, this is basically your placement group ID, where the result output set goes. These weights are the in-out map, the weight overrides or whatever in the OSD map. And then this stuff here I'll talk about later. But this will actually calculate a placement. So it sets up a couple of arrays here. So this result, these A and B arrays are basically the working set that I mentioned in those slides. All these temporary annoying variables. These are basically making copies of the tunables that are stored in the map that we're going to use for this calculation, all the way down here actually. and then we just iterate through all the different steps in the rule and we process them. You'll notice that all of these rule steps that customize the tunables for the specific placement just update that local variable, these local variables. So we can, for one particular rule, we can change the behavior of how the placement's calculating as opposed to doing it globally. But in any case, everything starts with take. So just take basically it's an assignment operator. It sets the working value to some particular, usually the root of the hierarchy. So assuming that the arguments for this step are valid, or valid device and bucket, or whatever it is, then we basically set a working array to have that one value with the length of 1. And then the next step is usually a choose. So one of these, either choose or choose leaf, and either first in or independent. The first in is meant for replicated pools, and indep is meant for erasure coded pools where you don't want things to move positions in the output. And so basically, based on that, we either get first in as 1 or 0, and recursive leaf is 1 or 0, depending on whether it's choose or choose leaf, and first in or indep. And then there's no output for this particular step. We iterate over all the items in the sort of the working variables, probably starting with just the root, and we'd go through and process it. So we make sure it's valid. If it's the first in case for replicated pool, then we set up some temporary variables and call into this choose first in function, which basically does all the work. Or if it's not first in, if it's an indep, then we call a different function for the erasure coded variant. And we pass in all the different arrays and sizes and all this stuff. It's all the tunables and so on. Fresh. And this we'll cover this one. I don't think I'm going to talk about the indep one because it's analogous. I don't think we need to get into that level of the code. But basically, this starts at one particular point in the hierarchy in our work array, and it generates a certain number of output items for that, and it's going to descend until it reaches a particular type. So maybe you're starting at the root and you're descending until you hit hosts. You want 3 distinct hosts, and so type would be whatever the type host is, or maybe you're going all the way to the leaves and you're getting leaves. But in any case, this sort of does one sort of step of that descent. And there's a whole bunch of nested loops here because, again, the original algorithm was conceived in a more complicated way than it needed to be. But basically, we have to find n distinct unique outputs of a particular type. And so we do this recursive descent. So we start out at the starting point, which is going to be whatever it is, the item. I think actually it's passed in. I can't quite remember. But in any case, we're going to do a recursive descent. There are a couple different, and then based on what bucket we're at, we have to use a different function to actually do that. So usually we use crush bucket choose to choose a set of items. But in some cases, we fall back to this permutation, which is sort of a degenerate thing. Again, this was sort of a bad idea in the original algorithm where it used to try to use the specified algorithm a couple times, and if it gave up, if there were too many local tries, we would fall back to just shuffling the items in the bucket and just using them in order. It turns out that was a bad idea, so in most modern cases, this path is never taken, and we always do crush bucket choose, but in some cases, that wasn't the case. So crush bucket choose is just a one decision at one node. So we have our input, our sort of random values, the place and group ID, and so on, and it gives us one item, makes one step basically, it picks one child for that. So if you look at choose function, basically it's just a switch statement depending on what bucket it is. It uses that particular algorithm. If you look at the straw to choose, for example, the straw 2 buckets, this is what every modern crush map will do. We basically get the array of weights and children for this bucket, and we basically just iterate over all of them. And so for every potential child, we the analogy here is drawing, or the metaphor is drawing straws. So we draw a straw of random length that's sort of based on the proportionally sized based on the weight of that child. So if it's a heavily weighted child, the straw is more likely to be long. So we calculate all the weights and we keep track of which straw was the longest, and that's the one that we return. And this is doing this exponential distribution. This is the newly conceived version of this algorithm that the Intel folks helped optimize back in like 2013 or something, way back when. That works quite well. So that's crash bucket choose. Let's see, where were we? We were in here. So again, we're looping. We're at a particular point in the hierarchy. We choose one child. And we see if we've reached the desired type. We're trying to get down all the way to hosts or whatever it is. And if we got to the right type, then we might keep going and continue our descent. We basically would loop again. If it's not the right type, we repeat. Otherwise, continue. We want to make sure that the item that we chose is unique. So if it's already one, if we already chose that in this descent, then we have to make sure we just retry, and we'll increment. Basically, this R value keeps getting incremented each time we retry, so that we'll pick a different random value. And other checks here, but basically, yes, we keep doing this descent. This code is super hard to follow because it's parameterized based on these tunables. So I apologize, it's very hard to follow, but it's probably easiest if you go through and say for a normal map, then this is always 0, these are all 0, for example, and then you sort of like prune out these branches. You could probably make a simplified implementation of this that only uses the default tunables, and then it would be more understandable. But yes, eventually you'll get down there. You'll have chosen another output item. Then you have to choose n of them, and so it'll repeat, keep going around the loop. And that is it. Let's see, do rule. Eventually, you'll go through all the steps of the crush rule to do the descent. And then at the end of the crush rule, there'll be an emit step that basically takes whatever's in your working value and it just adds it to the final result that's returned back to the caller. And that's how a mapping is calculated. So there are probably lots of questions there because I didn't cover exact the details. Are there particular parts of this that anybody is curious about, or is that a sufficient level of detail, or what do you guys want to see as far as this mapping part?
I had a general question, like those tunings, how often do we really need to change those tunings?
Never. So you basically always want to use the defaults, new clusters, which are sort of the current notion of like the best way to make this algorithm work. The only time those would be not the default is if this was a cluster that was created like back in Dumpling or Bobtail or something really old. And so all the data was placed in a particular way, and switching to the new tunables would just reshuffle the whole cluster, and people don't want to do that. And so that's the only time when they would be sort of not defaults. So these choose local ties, retries, and fallback retries were part of the original algorithm, and they were just bad ideas. They should basically just never be, you should never use them anymore. And that's, I think all of those are fine. Var was something that I believe a user discovered, where somewhere in this algorithm, if we hit a collision or a repeat event and it loops, we weren't varying R in a very efficient way, and so we would just retry a lot and fail before we finally got to an R that would work. And it turns out there's a better way to vary R so that it's more efficient and we don't have to retry as many times. So that's what that is. And then stable, similarly, was I think that was also a user, or I can't remember. One of these came from a user where they basically just tweaked the code a little bit, and it was way more efficient. So those, yeah, those are the main ones.
Yeah, I think the only ones I recall are I think choose total tries or something. We've in the past, I think,
yes, yeah. This is the only one, right? Yeah, this is the only one that probably a user would vary, and that's usually I think it defaults to something like 50 or 100.
Yep.
And basically, what happens is if you have a lot of OCs that are marked out, that array gets passed in here. That OSD will have a 0 in this weight vector, and that causes us to reject it. We're doing that choose here. That'll cause us to, let me find it. Somewhere here, we'll basically see that the weight was 0, and we'll reject. Reject will get set to 1. I can't quite remember. It's somewhere in here. Anyway, so if that happens, then you'll basically get lots and lots of retries. And if that were infinity, then we would you could mark all the OCs out and it would just loop forever, and that would obviously be bad. On the other hand, if it's too small, and you have a lot of OCs marked out, it'll just like not get a result, or you'll get like too few replicas. So it needs to be like big enough that for a cluster that has lots of things marked out, you'll still get a complete result, but not too big that it'll go forever. So
okay.
50 or 100 seems to be the number that we settled on. Okay, just a couple other things. So I mentioned that there's this this perm thing, bucket choose perm. So for each of these buckets, there's a choose function that will just pick an item, a child item, and the only one that I looked at was the crush2 one. Sorry, straw2 choose, because that's the bucket that we mostly use now. But for different buckets, its implementation is different. So there's a straw choose that uses the original straw algorithm that is sort of broken in some subtle ways that we didn't realize in the beginning. There's the tree algorithm that we never actually worked right. There's the list one that is not recommended, and there's the uniform one. The uniform one was meant, the original idea was that you might deploy like arrays of disks where the disks are all the same size and they're always deployed as a unit. Never like add new disks to an array because it only has 16 slots, and you'd only have them fail and you'd mark them out. And so it just sort of makes a really cheap calculation for that leaf layer of the hierarchy. And the way it works is originally it did some like weird modular arithmetic trickery, discrete math that like ended up not being super effective. And so it was replaced with this perm choose, which basically just the first time you encounter it, it calculates a random permutation, a deterministic pseudo-random permutation of the order of the items in the bucket, and then it just sort of walks through them. So like PR here is just the R parameter is modulo the size, and we would return that permutation position at that position, right? So this is sort of the fallback, just scrambling these equally weighted things. And it used to be that there's this thing where if we tried the regular algorithm too many times, this fallback local tries, if we tried it too many times and we just couldn't get anything, then we would just fall back to a permutation and use that. But that was just a bad idea. And so we don't, hopefully these settings are never actually used that way anymore. But that's how the original algorithm worked. Okay. That's the core for algorithm. Any last questions on that before I get on to all the weird stuff that we've added since then?
Are there any other things you had in mind that you might see changing in the future, or thought about adding but we hadn't actually implemented?
Probably not in Crush itself. I don't have any. Probably not directly in Crush, but I'll think about that. I have to my memory. Okay, so the next, there are a couple of features that we added right around Luminous that sort of made everything more complicated. The first one is shadow trees, and I'll show an example of that. So it used to be that if you had a hierarchy, a crush hierarchy that had like hard drives, SSDs, or whatever, you would have to create like you'd have to explicitly manually create multiple parallel hierarchies and have these rules that reference them. And it was just really tedious and annoying to manage. And so around Luminous, we added the ability to set a class on an OSD. So that's usually something like hard disk, SSD, NVMe, but it could be anything. And that would be sort of associated with the item in the hierarchy. And then you could have rules that would reference, I want to place this only on SSD OSDs or only on NVMe SSDs or whatever the classes are that you define. It turns out we figured out a way to do that in a way that was totally backwards compatible. And so when the crush map was actually compiled down and encoded and passed to a kernel, for example, the kernel client and mapping was placed, it would work in exactly the same way. There was no actual difference, but all the management tools and the way that you manage the hierarchy would have these types in them. And the way that works is that if you look at the tree of devices, each item has a type associated with it, and the weights, and it has a weight, and the weights still sum up some hierarchies. So this is a sum of all the items on the host and so on. And so that all was normal. But if you look behind the scenes at what the hierarchy actually looks like, it has these sort of hidden shadow items that are denoted by tilde and then the type. And so you have the main hierarchy that has everything of all types, including hard drives and SSDs. And then you have sort of hidden from the user, it has another hierarchy that has only the hard drives for the entire tree. And it sort of it has only those leaves, and then the intervening nodes have weights that sum only those items. So you have sort of a hard drive only root, and you have an NVMe only root, and you have an SSD only root. And then in the crush rules, when you write these rules, the take step used to just be take step default, but now you have this added optional part that specifies what class. And that basically means that instead of picking the default root, or the root for everything, it picks the root that only has the SSD items. So it's just this like easy notation. And when you decompile it, you'll notice that there are sort of IDs for all the different like shadow trees. So this is all handled automatically by the crush wrapper. So the user tools let you just add and remove stuff, and you only see sort of the main tree, unless you pass, like if you're dumping the tree, you pass show shadow and it shows you shadow things. But it's sort of, these are all automatically generated. And in fact, when you make a change, they're thrown out and then recalculated and regenerated every time. And so you never actually sort of touch these shadow trees manually. But it lets you make those per type roots automatically. So if you look in the crush directory, there's this crush wrapper class. This is the C++ class that wraps up all of the C code, and it has sort of the nicer complete interface for managing all this stuff. And it has, it's got stuff to deal with all the tunables and all this annoying boilerplate stuff. But in here, there are functions that somewhere in here, there's a function that basically rebuilds all of the shadow roots. So build roots with classes. This basically rebuilds all those trees after you make a change. So you would call, if you call something like set, like remove device, this remove. You remove an item from the tree. At the very end of this implementation, it'll rebuild all the shadows so it all matches up, and so on. But this class has all the functions for manipulating the crush map that are wired up to the CLI and the crush tool, so on. Questions about that? Let's see. So Gaurav has a question. If we have two classes, if the SSDs are full, will the complete cluster end up in read-only mode? That used to be the case. I believe it's no longer the case because I think we have instead of having a full flag for the whole cluster, we have a full flag on a per pool basis. And so I think when an OSD is full, we only mark the pools full that touch those OSDs. And so the hard disk pools, none of those OSDs are full, and so those should still be writable. That's good. But yes. Any other questions on the shadow trees? All right, so the other most complicated, annoying thing I think probably is the choose args. And so this was, starts here. So this was meant to deal with a case that we didn't notice for many years, an issue with the way that the algorithm is designed. So if you think about if you think about a hierarchy, like a weighted tree, where you have something at the root and you have a bunch of intermediate layers and then you have some leaves. All of the weights of all the items sort of sum up the tree so that when you're at the root and you have, say, a bunch of racks below you, the weights of those racks represent the cumulative sum of all devices that are nested beneath it. And so you can just proportionally descend the tree based on those relative weights, and you'll end up with the right eventual distribution. So if you do that, for 1,000 different placement groups or whatever, the amount of placement groups that are on each leaf actual OSD ends up being proportional to its weight. And it turns out that the math for that works out perfectly if you have that decision that's a perfectly independent choice. But the problem is that we aren't placing just one copy of a placement group, we're placing n copies. We usually, for a replica, we have like 3 copies or whatever it is. Erasure codes is even more. And so after you place the first copy and then you go back to place the second one, you can't place it on the same OSD. And so if we happen to pick that one again, we basically retry until we pick a different one. And it turns out that the probability math behind that makes that second and third and fourth choices no longer fully independent decisions. And it messes up the final distribution of items on the leaves. So in particular, the way that this manifests in the real world is that when you have some hosts or racks that have much smaller weights than the other ones, they tend to get too much data. So you might have like 5 racks that have, hundreds of OSDs each in them, and then you have one rack that you just started to fill up. You plugged in the very first host, and you set the weights proportionally or whatever, and suddenly those OSDs are going to be have way more data than they're supposed to. And so this was, it turns out there wasn't a sort of an efficient way to adjust the algorithm to take account for this non-independent probabilistic selection of those leaf devices. And so we ended up sort of working around it in a backwards way. Basically, the very first replica we placed, we used the weights as they originally were. But when we placed the second replica, we use a slightly modified set of weights where those OSDs in the mostly empty rack have a slightly lower weight, and so we have a lower probability of picking them with sort of the baseline algorithm, which because of its flaw will end up getting more, and it'll all sort of balance out. So we're basically just trying to compensate for that bias. And then for the third placement, we do the same thing even more, and so the idea is that sort of it'll net out in the end. So that's sort of the workaround for that particular thing. But the question was, how do we implement that in the algorithm? And the way we do it is by using something called weight sets. So normally a bucket has, where is it? And the straw bucket has an array of items, and then the straw implementation has an array of weights for each of those items, and we would always use that. The weight set concept basically is just an alternative set of weights for that particular selection. So this struct is just an array of weights that matches the items that we'd use alternatively for one particular choice. And then the choose args structure, ignore the IDs for a second. The choose args is basically an array of different weight sets. And so the first weight set would be the one that we use for the first replica placement, and then the second weight set would be the one for the second replica placement, and so on. And so as those weights would get more and more skewed for subsequent placements. And so this is just a way to store what those weights are, and they'd have to be like pre-calculated ahead of time when you generate the map, and then done that way. And then finally, so this choose arg thing would still be for one particular one bucket, one node in the tree, and then you have a map that basically has one of these for every bucket in the map. And in total, it basically allows you to have alternate sets of weights to use for different steps when you're doing your calculation. Questions on that? So the result then is that this crush choose arg map is passed into do rule. So in mapper.c do rule, we pass in this crush choose args, which is basically the array of all these for all the buckets. And then all of these functions, you'll notice, get passed in the choose args, gets parameterized all the way down, whatever, so that finally when you're doing like straw2 placement, for example, we have the choose args, and we actually go and we look up the particular weights for this particular selection. And this will either give us back the bucket weights, or if this choose arg thing actually exists and is defined and has a bunch of alternative weights, then we'd use that instead. When we did this, we realized we were basically fully parameterizing like what weights were used at what step along the way. And in order to sort of try to future-proof a little bit, we made this sort of core code also parameterize what the IDs were. So instead of normally you think of the tree having a defined set of children, it could be that maybe when you're in a different step of the way, you want those children to be in a different order or just different, or maybe you have some other reason to have like totally different parameters that you pass in that just have totally different tree structure or something. I don't know. And so we also made it so that you could parameterize these identifiers too. This is all implemented in the mapping code. So if you generate a map that does this, it'll spit out a result. But the code that actually manages the map, nothing implements actually creating these because we don't have a use case for it. But the idea was just to sort of try to future-proof it and put it in place in case we need it later. We wouldn't have to have some annoying compatibility problems. So that's how the algorithm does it. In practice, again, I'm not sure that we actually got all the way to using this. I can't remember to what extent the balancer does it. So there are basically two ways that the weight sets can be used. The first way you can use the weight set is to create what's called a compat weight set or compatible weight set. And that's a weight set where there's basically only one set of weights. This array here is only one deep. And we basically, instead of using the canonical weights that are stored in sort of the legacy tree, we have just an alternative set of weights that we use instead, and we use that for every step of the way. And the reason to use that, the reason why the compat weight set exists is because it allows us to run these optimization algorithms that make sort of incremental adjustments in the weight of different items in the tree in order to tweak the placement and so that you get a very even distribution. And so this is one of the modes for the balancer, where you can generate these compat weight sets, and it will run this optimization. It'll make all the PG distributions on the Ssds like very, very close, and it'll store it as a weight set with exactly one position. And the benefit is that when you encode the crush map for an old client that doesn't have support for weight sets or any of this stuff, it can just put that one alternative set of weights in the regular map in a legacy encoded map as the actual weights. And so sort of a legacy client pre-Luminous would just see a crush map with different weights, but it would just still sort of be a traditional old crush map. Whereas the newer code on the actual cluster, we know what the sort of the user specified weights for the OSDs are, which is their like supposed to be their capacity, and that's sort of kept tracked separate from the optimized ones that are slightly varied to like tweak the placement. So it used to be that was the default mode for the balancer module. I think we just recently switched that to the upmap, which is a different way of optimizing placement because it works a little bit better. But the benefit of having that legacy, that sort of, what is it called, Compat Weight Set mode, was that it would work with pre-Luminous clients, so older kernels, older VMs and stuff. It's probably not so much of an issue now because that was like 4 years ago or whatever it was, and everybody's upgraded their clients by now. But that's why it worked that way. But going back to the original goal of these weight sets, which was to handle this case where you had a rack with a small rack next to a whole bunch of large racks, and it would get too much data. I will be honest, I can't quite remember if we implemented all the code that actually generated these optimized weights. Actually, can't remember if we did that. Does anybody? Do you guys know?
I don't remember that. I think we might just be relying on the balancer to even things out at this point.
Yeah, I think we didn't actually do it. So it's kind of funny. We added all this complexity to try to like solve this in a like way, and we ended up doing a much simpler thing. So yeah, I think that's right.
The structure though there with the weight sets and like being able to vary that by position, that seems like it could be used for some kind of very interesting placement algorithm that might be like very different from boosting crush.
Yes. Yep. Yep. And I guess we succeeded in the sense that we intended to use this one way, realized that we could use it in a different way with the Compat Weight Set thing, sort of. Maybe that's I don't know. But yeah, we basically didn't end up having to go all the way down this road. So, and just when you actually decompile the crash map, you can see these choose args things down here. This is -1, and by the way, you can store multiples of these choose arg set in a map. I think they're associated with the pool. I can't quite remember how Ceph indexes them, but basically for any given bucket, you can have these different alternate weight sets. In this particular cluster, it's a Compat weight set. There's only one of these. This is just the slightly skewed weights for each of these buckets that vary slightly from the ones that are specified up here. But anyway, that's the main stuff I intended to cover.
I'm trying to think more about like what you could do with the weight sets piece, like what kind of placement policy what you might implement there that could be useful.
Yeah. I mean, you could have, they fully parameterize the weights, and so you could have different weights for different pools. So maybe you're doing some weird thing with trying to, if you have a pool that's IOPS intensive and another pool that's capacity intensive, and you're trying to like layer the two over the same set of devices and try to like optimize for both at the same time, so that you're balancing both IOPS and capacity. You might have different crush rules that reflect those different priorities, and then sort of tweak the weights that way.
Do something, especially with the primaries there, I suppose.
Yeah. Yep. Yeah. Yeah, I mean the fact that these, where is it, the weight set is based on which choice you're making. So where is it? So this is for one particular selection, and this is for position 0, position 1, position 2. We have all these different arrays. So it might be that this is the primary basically. So you might have one set of weights for the primary, and then this one is the non-primary weight, and you have that skewed so that the net balances out, even though you're sort of prioritizing primary selection in one particular place. You can do that. There we have sort of another mechanism in the OSD map that tries to let you sort of control the primary probability, but this could push it further down into crush.
Yeah, of course there's that mechanism in the OSD map if you want to directly control the placement of each PG without any kind of calculation.
Yeah. I mean, the challenge with crush is that it's kind of a black box. Like a number goes in and it spits something out, and you have all these knobs to try to control what the distribution of those outputs is, but you don't have very fine-grained control. And so it's worth noting that when Ceph calculates a placement, crush is sort of at the deepest level, but there's a whole bunch of layers of other stuff that are on top. So maybe it makes sense to look at those really quick, actually. First, look at where the OSD map calls do crush do rule. So it's this PG to raw OSDs, which is sort of the bit where we finally actually call crush. So it generates an integer from your pool ID and PG ID. That's that X value that gets fed in here. Figures out what the rule is and whatever it passes in the OSD weights and so on. But after we run crush, we remove any non-existent OSDs. Maybe the crush map doesn't fully agree with the OSD map, so it filters that out. OSDs. There's a primary OSD that gets selected, sort of in the degenerate case. It's the first item in the array, but it isn't always the case. We layer up map on top. So after we calculate the raw placement, we apply the up map exception list, basically. That might either reorder some of the results in the output array, or it might replace the output entirely. Let's apply up map here. Map and up map items layering. There's one other step in here. Maybe it's just this, to remove the non-existent. No, there's a step that also reorders the primary affinity. Yes, where is that called? Primary. So you apply the up map. You filter out the OSDs that are down, right? And then you pick a primary, and then you apply the primary affinity, which basically, for replicated pools at least, there's some probability where it'll just sort of, if one OSD is chosen as a primary, but it has a lower probability, it'll get bumped over to the right, and somebody else will be the primary instead. And so it lets you sort of push the primary roll traffic and the read traffic associated with it away from some OSDs that might be overloaded or something like that. Yeah. So you could imagine you could construct an OSD map where the crush map isn't actually doing anything. Like it could just be a empty placeholder, and you have up map exceptions for every single placement group, for example. That doesn't scale super well for really big clusters because this OSD map gets really big because you have a full mapping of every PG to every set of OSDs. But you could potentially construct something that way. Let's see. Other things in here in the crush directory that might be worth looking at. There's builder.h. This is a bunch of stuff just for constructing crush maps from C code. It's only used by the crush tool basically, or called by the crush wrapper. There's this crush compiler, which compiles and decompiles crush maps to that text format that looks sort of vaguely like C. And so this in here, there's a grammar for Spirit that describes what the language looks like, and the compiler basically goes through and compiles it or decompiles it back and forth. What else? Yeah, I don't know. Any other questions?
So I had a question. So from a user perspective, if they are not using the crush compact mode of the balancer, how much does weight set matter at the moment?
I mean, it doesn't matter at all.
Yeah, so it's literally okay.
It's basically, so the only user of it is the compat mode for the balancer, basically.
Yeah.
Yeah.
Mm-hmm.
Yeah. So if you don't have that mode, then it'll just be empty all the time. Yeah. But if you use upmap, was added in Luminous, I believe, and so you have to have a vaguely modern cluster. Yeah. What else? Yeah, I mean, there's so much like legacy crush in here. It feels like eventually there's an opportunity to like force people away from these legacy tunables, perhaps, as time goes by, and then eventually drop support for them. Same thing for these like legacy bucket types, like there's like the old straw buckets. I think those actually should all be gone because I think we just programmatically went and just changed them at some point. But like list buckets and uniform buckets, like these are all like mostly useless. The list bucket certainly, there's like almost no advantage to using this over a straw bucket. Maybe the uniform buckets because they're quite a bit faster. They just have this constraint where you have to have sort of a fixed size node in the tree. You can't add or remove items from it because if you do, everything will get all shuffled around. But if that were the case, then eventually we could like strip out a whole bunch of the annoying compatibility tunable code and like simplify a bunch of this stuff. I don't know.
Yeah, I think that makes sense. So over the years, you've gained some experience, and maybe the ones at least with which we know have issues, those can at least be removed. Things that may have potential to be, improved in future, maybe those we can still hold on to.
Yeah. So Matthew in the comments notes that it used to be that for the straw to straw 2 conversion, you had to do it explicitly manually during an upgrade. I can't remember if we decided to just do that for users if they hadn't done it yet.
I think there was a release where we said that you need to migrate to straw 2, and it was not probably automatic, but they had to. It was there.
They had a health warning if they didn't, but they probably were able to turn off the health warning. Like I suspect it's possible that there's still straw buckets out there. So we wanted to, we could just make that a hard requirement that they must remove the straw buckets.
Something we can check with telemetry, I guess, if there are any straw buckets out there.
Yeah. I can't remember if that is in the telemetry result or not. Function is just like so hard to understand. It's a bit of a zoo. Yeah. It did cause some community movement. That's why we didn't want to do it manually, I guess. But it should affect so few clusters now that it might be. I don't know.
I guess I have a couple of general questions if other folks don't have any questions. So one of the biggest concerns people have with Crush or like changing anything in Crush is data movement. So I guess what are the absolute no-nos with respect to Crush changes? And people should be really careful about whether they need to make this change or not, or this can lead to massive data movement.
This would be changes to the algorithm or changes to your Crush map?
Just Crush map.
Right. So the big no-no is don't change the identifier for a bucket. So when you decompile a Crush bucket, the first line there is ID -1, -10, whatever it is. Don't change that because that is one of the inputs to the pseudo-random function that picks what item when you're descending, doing that descent, the bucket. So if you have identical buckets, 2 different identical buckets, they'll choose different children for the same placement. So that ID has to be part of that input. But if you change it, then it'll just shuffle everything at that point in the hierarchy.
Got it. Yeah.
I think that, and yeah, use straw 2 buckets all the time. I think don't use the other bucket types. That's the biggest one.
Okay. Yeah, I guess my second question was, what kind of debugging tips do you have around the crush code? So if something looks like a potential, if something looks like a potential crush issue, how do you go about at least figuring out whether it is a crush issue or something else going on?
Yeah, so that's a good one. In the mapper code, there's this dprint k define that's commented out. So I basically comment this back in, and then I go and I compile crush tool. And then crush tool, you can do crush tool, and there's like test map pg, something like that, or maybe that's an OSD map tool command actually. But one of these you can put in the placement ID. I think it's OSD map tool that lets you do it. By my OSD map. Test the specific PG that seems to be problematic, and then you'll get a bunch of stuff to standard out that like lets you trace its way through all this code. See all these dprint k statements dotted all over the place. So that's my secret.
Okay, that is very useful. I did not know that until today. So that is great.
It's output like is really hard to follow because there's so many nested loops with like very subtle differences in like the parameters. So it's hard to follow, but that's the only real way to do it.
Yeah. Okay, that's good.
Yeah, and I guess the last bit of advice would be try not to, if you can get away with it, don't edit the crush map manually. Use the CLI commands. There's like a whole set of them, like the OSD crush, for dumping all the rules and renaming buckets and adding and adjusting all this stuff. Like there's all these things are in here. Try to do it through the CLI. And only if you can't do it, then edit the crush map, but also probably tell us that there was something that you're trying to do that you couldn't do through the CLI, because then we can go and make it so it is possible. So all these things are also possible through the OSD map tool. Should all be that let you add and remove items or whatever. The OSD map, or sorry, not the OSD map, sorry, not the crush map, the crush tool lets you add and remove all these things. The crush tool also has this test function, which will calculate over a bunch of like synthetic inputs and give you like a distribution of outputs. And there are also, you can do that and you can do show mappings, and that'll show you every input it tried and the actual output it got. So one of the things you can do if you want to test some major change to your crush map, you can pull your crush map out of the cluster, use the crush tool to make some modification or recompile it or whatever, and then you can basically run test on the old map and on the new map and compare the placement and see how much it's changed. So you can do show mappings on the old one, show mappings on the new one, and then have diff count the number of lines that are different, and that'll give you some sense of like how much data is going to move. Yeah. I guess that's it. Anything else?
Going back to the earlier question about any other feature improvements you see, is there anything at the higher levels besides outside of crush?
I mean, I think this idea, this process I just described of like seeing what a change would do to your data movement is like kind of tedious. You have to like extract the file, modify it outside the cluster, and do some simulations on it to see what would happen. It would be nice if there was a way to do that in a way that wasn't so tedious. probably involving some other tool that kind of tries to automate that process. That might be nice. It might be that in certain cases, well, I guess the optimizer, the balancer, there are opportunities there to improve it. I guess there was a thread on the dev list earlier this week or just recently about our current optimizer optimizes on a per pool basis to get plus or minus the right number of PGs on every OSD. But it does that independently for each pool. And so it might be that across a whole bunch of pools, you end up with OSDs that have too many PGs. And so we need sort of like a global optimization as well. That's something that we can certainly do. The optimization balancer stuff also it looks at PGs primarily, and it doesn't look at the sort of actual net usage of space, which might vary from the sort of expected usage versus the actual usage. And I think that still isn't taken into consideration. Yeah.
And I guess there's some other usability ideas that folks have had in the past as well around like JSON format input and output for a crush. So you wouldn't have to go through a bunch of these individual commands to edit the map.
Yeah, that would be nice.
Yeah, I just added a link to a PR. There was this recent wrapper tool called Crush Diff that got added. So it's a wrapper around the Crush tool and OSD map tool, which makes things a little simpler than earlier.
Yeah, right. Yeah. Yeah.
It would be good as well if Crush tool would understand JSON as well. Because right now it's really hard to manipulate. Like you can get the output like of the Crush map in JSON, but if you want to map it to, let's say, a Go type, and then unmarshal it to a Go type, and then remarshal it, then you cannot really import it or manipulate with Crush tool. So that's
there is already a dump, so you can dump the Crush map as JSON. So I think really all that's needed is a undump, whatever. That'll just parse the JSON, come back in.
Yeah, but it's like when you have the JSON, then you have to compile it and then re-inject the map.
Yeah.
That's the case where you cannot work with the comments. So I have a long-standing tracker for this.
There's a JSON spirit library that's already in the tree that we use for parsing JSON. So it's totally possible to go and write that. But yeah, somebody needs to go do it. But yeah, that's probably nicer than that sort of weird domain-specific language.
Yeah, because it's plain text and it's really hard to parse stuff. Yeah, common data structure is always good.
Yep.
For other consumers, at least.
Cool. All right. Everyone.
Thanks, Sage.
Awesome. Thanks, Sage. Really useful.
All right.